Right. Good morning. Welcome to another session. We continue from where we left off, where we discussed minimization, canal maps. Who is that? Tafadhali Wakarimazondo. Be very careful. You might find yourself out of. In fact, you're already out. All right. Right, we continue with where we left off, where we discussed minimization. I think we saw it necessary to minimize circuits so that possibly they become more efficient, use less equipment, which considerably cut costs for building circuits. We discussed one way of doing it, which is by using the laws, the Boolean algebra. There are laws which you can use to minimize the circuits, but they are effective to a certain extent. When we have plus 3 or 4 variables, it becomes very difficult to use Boolean algebra for simplification. And that is where we introduced the canal map. We did a few examples. And I think I only mentioned the sum of products way of using the canal map. There is another one, which is the product of sum way, where we consider the zeros. We group the zeros. Right. I gave an example last time. I'm not sure if it's the same example I'm giving today, but either way, we move. We have another example today. We have a three variable example. 0, 1, 0, 1, 0, 1, 1, 1. Right. We have f of is equal to sum of products 1, 5, 2, 6, 7. And we want to simplify for those outputs. We want to simplify, we want to get a simplified circuit. How do we do it? All right, we will draw our canal map. We know that for each output, we have a square in the canal map. And here, I already mentioned this is a 3 variable circuit. So we can represent it as, let's say, F, A, B, C, 3 variables. And we already mentioned the meaning of this kind of notation. You can go directly from these values, knowing for the values which are given here, the mean terms leads to output 1. The mean terms in that kind of notation leads to output 1. Without going through the truth table, we can go from this kind of notation directly to our canal map. If I was to draw a truth table, I will have A, B, C, nope. With the 0, 1, 0, 1, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, without order. But I think you've been following, you now know the order of things. So we have our F. For the first value, we have M0, which is 0 because it's not there. The second value is 1, we have 1. Second value is there, M2, 1, this one. M3, 0, 4, 5. So we have 4, 0, 1, 2, 3, 4, 5, another 1, 6, 7. Your truth table will look something like this, where you have your M0, M1, until you get to M7. So for each output which is 1, it is included here for the special kind of notation which we call sum of products notation. So if I'm to draw a truth table, it will be like this. But if I am asked to simplify, I can directly go to my Kano map, put my ones and zeros, knowing for the values which are in the table. In the notation, there are ones. I can predict the zeros. So we have 0, 1. Yeah, we have 0, 0. We have 0, 1. We have 1, 1. Then we have 1, 0. The order at which you give these values here is very important. It is defined by the gray code. I think I already mentioned that. We have a chart, say output F, I want to say output F. Output F, I want to go from our truth, from our notation. I gave you a notation. Let me be clear with it. I gave you this notation here, what we have here, right? And I said you should minimize it. One way is going through the truth table. How do you get the truth table? For the truth table, we have the values 0, 1, 0, 1, 3 variables, 8 outputs, 1, 2, 3, 4, 0, 1, 0, 1. So 0, 0, 1, 1, 0, 0, 1, 1, 1, 2, 3, 4, 1, 2, 3, 4. These are the values of our 3 variables. These for 3 variables, these values, they don't change. It basically remains the same. Now for the output, we know that this is M0. This is our min term 0. This is our min term 1, 2, until we get to our min term 7, the last one. This special kind of notation shows that for min term number 1, the output is equal to 1. Min term number 5, the output is 1. Min term number 2, the output is 1. So for min term number 0, which is not here, the output is 0. For min term number 1 is there, the output is 1. Min term number 2 is there, the output is 1. Min term number 3, 4, not there, so we have 3, 4, we have 5, we have 6, we have 7. This is how we came up with the output F on the truth table. It began with F being defined by the sum of products notation. And this is how we came up with the truth table. I'm hoping the question was answered. Now, continuing to our Kano map. This is how you represent a Kano map with 3 variables. Others, they can do it like this, A, B, C. It always brings out the same result, believe me. With practice, you get comfortable with one way of doing things, and it sticks. This is my way of doing things here. So, meet yourselves, unless or otherwise. Gerard Chingwe, meet yourself. Right. So, how do you input the values either from the truth table or from the notation into your Kano map? Directly from a Kano map, I know for position 1, position 5, position 2, 6, and 7, those are ones. How do I identify those positions? Position 1, this is 1 in binary, 0, 0, 1. I find my 0, 0, 1 here. On the Kano map, how do I find it? I have 0 here, 0, 1. So this box represents 0, 0, 1. So it means the output is 1 here. Then I have, if you can help me then, unmute yourselves. This box, participation, this box, what value do I have?
0,
I have 0, yeah,
0,
0,
0,
0,
1,
1, yeah.
1. See,
Okay,
The last one is 1.
this is 1 in the here.
yeah,
This box,
0,
0,
0,
0
1,
here,
1,
1, 1, 1.
1.
Well, and with those participating knowing exactly what I'm doing here. If you don't, it means you are missing something. You can as well ask in the group to understand how we came up with this Carnot table. From the Carnot table, we go to the simplification. How do we simplify? Simplifying starts with identifying groups of ones. The groups of ones can either be in pairs, fours, eights, or 2 to the power of n, where n is greater or equal to 1, I think. 1, 2, 3, yes. Where n is greater or equal to 1. So you start identifying the largest group first. So if you have a group of 8 ones, that is the first one you use, then you use another group of 4 ones, then a group of 2 ones, a pair of ones. All right, here we don't have a group of 8, we don't have a group of 4, but we do have a group of 2. So we can make a pair. This is a pair right here. I think this is the exact example I did. We have another pair here. We have another pair here. And lastly, we have another pair here. We have made 1, 2, 3, 4, 5 groups. 1, 2, 3, 4, 5 groups. Yes. From pairing, once you are done with pairing, then you go to the simplification. So F can be simplified as, how do you read your pairs? You find where the variables remain constant. You find where the variables remain constant and you input those variables. So starting with this one, starting with this pair, can I put them in colors? Starting with the red pair. Voila. How do I read the red pair? So when I say the variables remain constant, you look at this side and you look at this side. So when I look at this side for this pair in red, my variables change from 0 to 1. It means I don't consider the variable a in the simplified expression. But if I look at this part, if I look at this part, the BC part here, I see that the variable, we have a chart, I see that the variable remains constant. Is it always we should have 4 pairs? I'll answer that soon after. All right. So if I look at this direction where we have our loop, our group, I see that this is the column. This column remains constant. There is no change in the variables. Only one column, it means there is no change. Here we changed the rows. Here we didn't change anything. We didn't change our column. So that's the meaning of variables remaining constant. Right. So when the variable remain constant, here we have B, C, B bar C, because this is 0, 1. 0 in its complemented form and 1 in its uncomplemented form. Those are the rules for sum of products. So for the first value in our simplified expression, we have B bar C. Right. If we then go for this second one, what remains constant here? This row remains constant, the row with A is equals to 1. It does not change for the loop. The rules I'm teaching here, they remain the same even for a 4 variable Carnot table, 5 variable Carnot table. The rules remains the same. You group, then you see how you simplify from the groups. Right. For this second one, A is equals to 1 remains constant for this loop. A1 remains constant, so we have plus A, which is 1. Right. There's another thing which remains constant here. When we move from column number 2 to column number 3, something changes there. When we move to column number 2 to column number 3, so we have 1, 2, 3, 4 columns. So when we move from column 2 to column 3, a variable changes. 0, 1, it changes. We don't use it. 1, 1, this one here, and this one, it does not change. So it means we can use it. What is the variable 1, 1? The variable is C. So we have AC plus, if we do the same for the rest of the groups, we will get B bar C plus AC plus AB plus B C bar. If we continue grouping those two groups, we will get something like this. All right. Now to the questions. Someone asked, say, by grouping up, or can we group one array? All right. I'll start with that. Yes, we can. For example, the assignment I gave you, there were groups which had only one is a member of that group. And that changes everything. That changes, it also changes here. So it means one can also be considered as a group. So instead of having n greater or equal to 0, we have for all values of n is greater or equal to 0. So when we have n is close to 0, we have 1 as a group. One example, we can have something like this. This is our kernel map. A, B, C, 0, 0, 0, 1, 1, 1, 1, 0, 0, 1. We can have a kernel map like this, 1, 0, 0. We have a kernel map like that. How do you simplify that? You just identify your one as a group, then you find the variables which remain constant. So if I'm finding the variables which remain constant for this one, we have this and this. All of them, they are remaining constant. This row, it does not change for my group. It remains 0. So it means if this is my F is equals to A bar, because this is a 0, A is represented as a complement. Then here we have BC, BC, B bar, B bar, C. This column doesn't change as well. So it means my F, if it was a simplification, then it could be simplified into something like this. So for a 1, which is not grouped at all, which does not belong in a group of 2 or more ones, how do you then solve a case like that? You just find where the variables remain constant. And in this case, A bar, B bar, C, those are the variables which remain constant. This was very crucial in the assignment I just gave you. Right. Is it always we should have 4 pairs? Another question, is it always we should have 4 pairs? Which 4 pairs? I'm hoping I answer the question. Is it always we should have? In this question, we don't even have 4 pairs. It's not always. I'm hoping I'm answering. I don't get the question. In this question, we don't even have 4 pairs. We have 2. Francis, yes. Question.
Per final output you do on F there.
Yes.
I realized something between A, B, and AC. They produce the same output. We can only choose. Still gonna choose a one. And
A, B, and AC.
yeah.
They produce the same output. What does that mean? Where is our AB here?
I can on 111.
On
The output
111.
111.
Okay. Here.
Yeah.
This is our what? Remains constant. A.
That should
This is our
be
AB, right?
AB.
We have
Yeah.
our AC, which is here. What do you
Uh,
mean when you say they produce the same output?
isn't it they're all defining the output here 111. AB is the definition output here paper 111. Then AC is also a definition output here 111.
I don't think so.
Uh,
In fact,
I think that's the thing. Because isn't it when we're looking at it to simplify the output logic here, look. So when we input my values are 000 into the logic, find our output F, we should get a zero.
okay.
So if we do that for the output here 111, we see with the AB, where to get output here, do a B bar C plus
Uh,
AB plus BC bar, who will get the same output F without having to have AC. Or if we replace AB with AC, we still get the same output.
so does it mean we can simplify this further? What
Yes,
what what will
that's what I
wait,
mentioned.
what will it look like? AC. We remove the AB,
Yeah, yeah, and leave AC.
or we can do this. B bar C. I will have to confirm this because I'm still calculating it, analyzing it in my head. It makes sense though.
Yes, that's
It makes sense.
because
Uh,
when I tried to do the Boolean algebra, in
uh,
the final answer, it came out as B bar C plus
uh,
BC bar and ABC.
okay. All right. I think I get the point. Now I get the point. I think that's another thing with using Kano maps. Once you have made groups of all the ones, there's no need to repeat a group, right? For example, here we repeated a group here. We said we use this one, we use this one. Okay, we are only left with this one. But it's much better if we pair it with another one. So what we did is we paired it with this first. It should have ended there because all the ones are paired. However, we continued and we paired it again. That's why there is a repeated answer here. Thank you very much. Who was that? Francis.
Alison.
Yes.
Well, thank you very much. I think that's another thing which we can get from this question.
Alison.
Yes.
Isn't it kuti like pamagroup apa pamataura pamagroup atatu apo kwangogroupa the only one side then inongobuditsa semanta rather than kugroupa ari 2 kana kuzoipea iri 1 chete.
Exactly.
Because pane panaka
That is exactly what I'm explaining. What you need to do is to make sure all the ones are grouped. But here what we did, we made sure all the ones are grouped this stage, but we still continued and grouped, made another group of already grouped ones. That's why there was a
true.
repetitive here. You get it? So
Yeah, I get it.
once you've grouped all the ones, then that's it. You don't have to make a lot of groups because it will just be giving out the same output as Francis already mentioned. Thank you very much. It seems people are doing something out there. That is learning. That is learning, not just standing and waiting for Mr. Madongo to lie in your face. Thank you very much. All right. So here, this is the sum of products way of doing things. The product of sums, you now identify the zeros. It's the same. You now identify the zeros. So we can start by changing it here. This is the sum of products. So if we are now dealing with the zeros, how do we change the notation? Anyone to help us there? How do we change the notation if we're using product of sum? How does F change? What do we have inside there?
0,
0,
3.
1, 2, 3, 4, 5, 6, 7. Like this. When we are now using zeros, this is the notation we use, product of sum. Now, the Carnot table, it will be the same. For the values, max terms, for the max terms, this is sum of max terms. Now, this is this sum of max terms or product of max terms? Product of max terms. Right. For 0, 3, and 4, we have 0 here, 3 here, 0, 1, 1, and where is 4? We should have another 0 here. What happened? There was a 0 here. This is a 0, yes, 4. Right, this is our Carnot table. Now, when we are grouping zeros, so we have this group here. It's also minimization. Then we have this one. It's also minimization. You use the same way we used to find the simplified form, find the constant variables, and you apply it. So for this one, f is equals to, what is constant here? A is changing. So what is constant is B, C. When we talk of product of sum, this is the sum part, and it's a product of something else. What becomes of a 0 in product of sum? A 0 remains as it is. A 1 is complemented. It's sort of the vice versa of the sum of products. So a 0, we no longer put a bar on top of it. It remains like this. B plus C from here. This is where it remains constant, BC. How do we represent it here? Is B plus C is a product of this one. This 0, what remains constant is ABC. ABC remains constant, ABC. Where is our bars here? This is 1, 1, this is 0. So we have something like this, A, B bar, C bar. Anyone having issues with how I came up with that formula right there? Nope.
Me.
Yes. What's your question?
I do not understand.
Right. When we talk of product of sums, there are two ways of representing expressions in logic design. We have the sum of products, which is what I frequently use. I think this is the easiest, sum of products. So when we talk of sum of products, an example, we have something like AB plus AC plus BC. We have sum plus of the products AB. This is the product, sum of the products. We have the product of sum. Its representation is something like this: A plus B, A plus C, B plus C. These two things are not equal. I'm just demonstrating what a product of sum, or what a sum of product expression looks like. So this is the product of sum. What we have product, this bracket, of the sums, a product of the sums. How do we get here? You identify the ones. You identify the ones for the sum of products. Each value which has a 0, it is complemented. When we mean it's complemented, it means if A is equals to 0, how do you represent A? A is represented as A bar in its complement. 1 is not complemented, it remains as it is, complemented. It remains as it is. So it means if A is equals to 1, how do you represent A? It stays like this. But this is the opposite here. Here we identify zeros. We identify zeros. Our 0 remains as it is. So which means A is equals to 0. It is represented by A. However, 1 is complemented. It means if A is equals to 1, A can be represented as A bar. So in our case here, on our Carnot table, how do I remove this? So in the Carnot table we were using, step number 1, we identify the zeros. We identify the zeros, we group them, we just identify these are our zeros. Pen. These are our zeros. We group them. So this is my first group. This is my second group of 1. Once you've grouped them, then you go to the expression. When you go to the expression, it should be in the form of product of sum. So what do we have here? You identify the constants for this first group. You identify where the variables remain constant. When we move vertically on our Carnot table, it is not constant. The variable A changes from 0 to 1. So we don't consider A in our expression. But when we move in this same group, in fact, we don't move. This BC with 0, 0, it remains constant. I already said 0 remains as it is. So it means we have a B plus a C, which remains and not complemented. All right. In other ways, I can do this for understanding. When I'm using product of sum, this value here, this is B plus C, this is B plus C bar, this is B bar plus C bar, this is B bar plus C. If I'm using sum of products in red, if I'm using sum of products, this is what? This is BC, this is, no, B bar, C bar, this is B bar, C, this is BC, this is B, C bar. So this is A bar, this is A, and if I'm using product of sum, if I'm using product of sum, this is A, and this is A bar. That can help for understanding. Right, so continuing with our expression, we just dealt with this one. We took B plus C because this 0, 0 remained constant. Then for